this is going to be a little bit of a change of pace. The observation, those of us doing observations in the world have kind of lost our lives since Gaia released the DR2 catalog. It's been an amazing journey, and what I want to do, we've got some great results, and I'm not going to talk a lot about that, but I'm going to talk about what the promise of what we could do if we were suitably motivated. And in particular, trying to answer questions about solar system formation. I want to try to give you a quick rundown of the thinking that I have been doing the past few years. So all of this, of course, basically started for me with the ARCOP application that we successfully observed in July of 2017. We were trying to characterize this object before New Horizons flew there, and from this light curve, the instant I saw it, to me that screamed contact binary. Took me a little time to prove it, but this is the power of having just a fairly small number of data points on an object. And that shape has really kind of revolutionized how we're thinking about solar system formation. And I'll talk about that a little bit more here in a second. But, wow, the picture disappeared. This is my favorite picture in the universe. It's this one right here. What's supposed to be here is a nice big one. But in any case, it's the morphology and shape of ARCOP that is the key critical components of that. And while it would be nice to get a really big survey of these cold classical objects with spacecraft, that's just not financially reasonable. And occultations are a much cheaper way to tackle this particular problem. But it's a lot of work. So here's the team, and that back picture's clipped off at the top. This is a very large team that it took to get those few data points to show that contact binary shape. A year later, we had a different team in Senegal that helped confirm the contact binary nature of this object. One of the key aspects of these teams that we put together here is that very few of these people are professional scientists of any stripe. They are community members, they're students, they're people who are just interested in being involved. And the pattern that I put together includes training and getting people out in the field to collect this stuff. It's a very, very profound experience for everybody that's involved. There's an amazing sense of community that's built up in here. And it has interesting societal implications that I'll touch on at the very end. But ARCOP, to me, opened up a new exploration pathway for understanding our solar system by looking at these small bodies in this primitive, undisturbed reservoir of material in the outer solar system. And to recap very, very quickly, and this is well worth reading in detail, these papers that have come out of this particular community. I've been working with David this morning because he's just down the hall from me. But it all starts with the streaming instability, where you have material, and the material is kind of moving up through this picture, and just from vortex instabilities, you end up with clumping centers that grow in a creek, and you create this material. The next step, you end up with these clumps that start to self-organize and collapse into disk structures. And it's this component of collapsing from the crowd, and you've got a lot of angular momentum, and it is a natural way to create these shapes that are ovoid as opposed to spherical shapes. And in the end, in this particular clump, is going down to a binary object. And then the final step to make ARCOP is you bring these pieces together. And the fact that they're not disturbed, they're just sort of very gently resting on each other, it meant it was a very low velocity, low energy combination of those two bodies. And that constrains how you evolve the solar nebula. And so getting more information about this is going to be absolutely key. Now, I'm working up to a bigger project. In the meantime, I'm doing a lot of support work for the Lucy mission. We've got these 5 targets that we're working on getting ready for these particular flybys. I've been doing occultations of all of these objects, and a big surprise for me came out of the observations of Ptolemy. Here's the first 3 occultations that we did, and after the first 2, I didn't know what the heck I was looking at. By the time we got to the 3rd one, I started to realize, oh, it's a low amplitude light curve object, and it always looks elliptical. It's got to be oblate. And in fact, we have, I'll come back to that in just one second, there's 2 more occultations. This is actually the case. Lundley is an oblate object, very similar in size and aspect ratio to Aircroft's large lobe. And we found a satellite. There's a satellite right here to show the whole system at a scale. It turns out that this part of the system is very similar to the large lobe of Aircroft, and the satellite is about the same size as this. To me, it looks like Lundley is the same thing as Aircroft, but it just never merged. So we're continuing to study the Jupiter Trojans because they're easier to do right now. They also represent an endpoint that will be interesting, but we still really need to get back to the source material, and that's the cold classicals. So by understanding and characterizing the population of these objects, we can provide more constraints in the formation models, and we need to know things like how common are contact binaries. Are they always contact binary? Is there some, are they always oblate shapes? Is there an upper size limit to objects like Aircroft? In other words, you get up to 60 kilometers, is everything going to be basically spherical, or they still have some oblate nature to it? And the list of questions goes on and on. It's really kind of amazing how well these shape measurements will tie back into the hard constraints on formation models. The coolest thing about the occultation stuff is it basically is the resolution you have is to first order in this size range of object is independent of distance. Unlike all the other normal things, like imaging and photometry, it gets really, really hard to do this work in the solar system, and you need massive telescopes. Occultations can get by with fairly small apertures. And the other thing I would point out, with the new Gaia catalog, we are now at a point where if you're interested in any solar system object that we know about, and you want to learn more about it, you can go out and learn more about it. Nothing is closed off from this. The only challenge is there's a lot of those objects out there. There's only so many of us. And so you have to be a little bit more targeted and specific about the kind of questions you want to tackle. But so here's my approach for how you do a cold classical object. This is the reality of it, is that the very first occultation is hard. You've seen the examples of that already this morning. You're trying to get just one chord to tell you that the object's roughly there. And that will give you already astrometry that is limited only by the Gaia catalog. So we're talking about hundreds of microarc seconds, even from a single chord result. So imagine sending a team out. First one, you get a range find. You collapse the orbit errors a little bit. In the next campaign, you get a few chords. Now you start to get a little idea of the rough shape. And but you're also getting astrometry. And then the third time, after you've got 2 sharp, good measurements, you can generally start to put these campaigns out there and get like 5 to 10 chords across an object and start to really, really hone in. And you're still getting astrometry. Combining the astrometry from 3 events gives you a pretty good detector on unseen masses. If there's a barocentric wobble due to something you haven't found yet, this puts pretty tight limits on the extra mass that you can have out there. Every time you do one of these campaigns, you're having an opportunity to find another companion. In fact, one of the best ones is going to be during the range finding time. You're going to have stations spread out, and you're not focusing quite so much on the object itself. So we know that this is all kind of built from the experience I've done with Lucy and just scale to the astrometric uncertainties that we have on TNOs. And it sort of represents the minimum set for doing a good job. So what's coming up? You've heard a lot about VRO and the LSST, the survey is coming up. We are going to see a lot of new TNO data. It's going to be really, really good astrometry. The number of objects we have to draw from to study this way is going to increase drastically. Right now, what we know is the population of known objects with good orbits is kind of small for getting into a really detailed survey like I want to do, but that's going to change. Also, as soon as Gaia stops observing, the catalog starts to degrade because proper motion errors would propagate as a function of time into the future. So if you were saying, well, we'll get around to it in 20 or 30 years, it's going to be a lot harder in 20 or 30 years than it is right now. Okay, so I've done a point design on a survey that I would love to do. And I picked this more for its shock value than its practicality, but it's not that far off. So I want to do 1,000 cold classical objects, just cold classicals, and get 1,000. That's 3 events per 3 occultations per object. That's a total of 3,000 occultations, down to a minimum size of about 20 kilometers. And the goals would be good shapes, binarity, contact binarities, close binarities, collision. And the collisional history comes from how smooth is the object. You see big bites taken out of the edge and the limb. And as I said before, this is kind of for each one of the objects, that's what you do. This is a very large program. This is comparable to the cost of a Discovery class mission. But if you think about the science that can come out of that, I think it ranks pretty well against the mission. The problem is, programmatically, we don't treat ground-based occultation surveys where a bunch of amateurs running around with quite the same way we do building a spacecraft. And that's one of the things I'm trying to do is to raise this as this is something that we can do. Now, this is a 10-year effort minimum. That turns out to be an average occultation rate of 1 per night, which is really scary when you think about it. But you can spread that out to 20 years and I think you're still doing just fine. But this is to help frame the discussion. So this kind of wraps up the parameter space that we're working in and what the occultation survey is attempting to do. So I've taken the known trans-Neptunian binaries, that's all dynamical classes, represented by the black triangles, and I'm zooming in on the corner of this diagram. Here, it's the separation of the bodies divided by the radius. So that's a measure of how deep in the hill sphere you are, or the stable region, plotted against diameter. And this one is a dynamical marker, and this one is, I need to know diameters because that tells me how to design an occultation observation. So the occultations kind of work in this green box here. The higher up you go, the harder it gets because there's more ground you have to cover on the Earth to measure the objects, but you get both components. But so there is stuff to be had up here. Note all of these black triangles up here, most of the population we know about, is much less tight than where we're going to probe the occultations. But we know that parameter space has stuff going on in it. This is the New Horizon object you heard Ann talking about earlier in the meeting. This is also a binary that was discovered by the Recon Project. Rodrigo published a paper about that. And then we have these 3 Jupiter Trojans. All 3 of the 5 targets are actually binaries, and they're all tight systems. And then we have air plotting down here. So what we want to do is with the surveys kind of fill in the zone and provide the guiding information by the formation models. So these are some of the things that we can address with a survey like this. Is on the left, what I have is what's important to the modeling. And on the right is what we have that we can use the occultation data to constrain the calculations that come from modeling what's going on in the early solar system. Binary fraction from merged bodies out to the edge of stability. And you'll notice, I should point out, this is kind of shows you the resolution limit of the best angular resolution telescopes we have, Hubble and James Webb. And those systems are all blind to what's going on down here. So it's kind of filling in the last piece of that parameter space. We want to get 3D shapes of small bodies and how much collisional processing, correlations between duplicities and shapes. Also, I should point out that this does require kind of a statistical approach to getting population statistics, because we always see TNOs that say, in our lifetimes, you get one viewpoint on TNO. It's not like with the Jupiter Trojan, the main-belt asteroids, they orbit the sun, and you can look at them from all different sides and kind of work out the 3D shape. You have to do this statistically in the Kuiper Belt, which is why you need a big survey to be able to unravel that. We've learned that lesson over and over again with the dynamical structure of the Kuiper Belt, and this is a lesson that we need to carry forward in the physical characterization. So in conclusion, I believe that a large survey of gold classicals is an extremely important task that we should all as a community take on. This is a really big project. I would love to help start something like this, and I'm doing what I can to raise awareness. I'm doing a lot of writing and trying to get people out and understanding what we can do here. As I said, we need a large sample. The biggest challenge is funding support, and it's not just that the money isn't available, it's that there are no programs that have money that do this kind of thing. So one of the things that I'm looking at is trying to go after more philanthropic sources and also sources of funding that are more about societal impact. If you think about this, that point design there would have me involving 180,000 observers to collect that data set over 10 years. You think about any big, major scientific task, a research project that we have ever taken on, and I'm not aware of anything that comes close to that scale directly involving non-scientists. And I think that is maybe one of the selling points that I can use to get philanthropic donors interested in this, because it's not just about the science, it's also about affecting people's lives. So with that, I will stop and happy to take any questions. Thank you.
It's amazing to hear about your vision, and I'm tempted to ask more about how you see the societal impact, but I'll ask about something else scientific that caught my attention. You were saying that you envision the survey to have a large impact on our understanding of the collisional evolution because of the strange shapes. So if you have things that look like they're chipped off, but I think that you said that you're going to probe down to very small sizes, down to 20 kilometers. And where are we in our understanding at this point? And I don't know this. At which sizes do we start expecting to produce episodes at these densities, the gold classicals?
Right now, all I can do is to look to the Jupiter Trojans for guidance, because that's where I have the most data at this point, thanks to the work for Lucy. So we have 5 objects that range in size from 20-ish kilometers up to 120 kilometers. Every single one of those shows evidence of having been collisionally processed, which you expect. The collision rate is higher in the Jupiter Trojans. However, the existence of polymorphy says that you have not yet erased the primordial shape completely. The oblate shape still survives. So I take that to mean that what we're going to learn from the Trojans in the near term is going to be something that we can use to also backtrack the collisional part of this process. And again, it's all statistical, but frankly, my own prediction would be with the cold classicals, you're going to find lots of binaries, contact binaries and such, but you're not going to find so much evidence of collisional processes.
So, Mark, would you want to say something about like what facilities you would need or use for this program?
Well, my vision for this is that you would have clusters of 30 telescopes that would kind of live together in whatever country that they're planted in. So you could have like 2 sets in Australia, you could have 1 set in Japan, 3 sets in Europe, whatever. You just spread them around the world, places where it's good to be observing. And then you run those crews independently. They're independently staffed to take care of the equipment. And then you bring people in for a campaign, you train them, you go off and you do the thing, and you just have this parallel processing of just events happening all over the world, running with local crews, so you're not shipping equipment around. So that's the concept. Also, 80–85% of the cost in my point design was taking care of the observers. The infrastructure to run this is actually fairly modest. But we can use robotic telescopes to kind of take care of that first campaign and just do that, just chip away at that and have a couple of good networks out to chip away at it. And maybe that would cut the cost probably 30%, just doing that.
Great talk. Over here. Regarding the Sean occultations, have you detected it enough times to determine its orbit?
Oh, it's such a sad story. We saw it the first time. We tried doing it again, and we did this massive campaign in Kansas. In fact, if you read Sky Telescope, you can read all about our thing in September last year. I put an article in there about what we did. We found it again. And basically, what the problem is the time base between those 2 occultations is such that we don't know. It's like, is it 100 revolutions or is it 101 or 102? And if you knew what the density was, I can tell you exactly what its orbit is right now. But we don't know that. So we had a 3rd shot, and it's our last before encounter, in Mexico in February. We had a great team down there. It was almost all run, the observers were all Mexican students. We brought a few observers from the United States to help out, but Ivy was there. It was a great time, but unfortunately it's private. So we're not going to know the answer to that question until probably, my guess is we'll start to figure out what's going on about 2 or 3 weeks out before encounter. So I'm working on plans for using Lucy itself to solve the problem going in.
I really enjoyed the talk. I was wondering, what do you think about Helios? Could they use as a proxy of friends of Japan Trojans or transmission intelligence? I think I read the paper that saying there are so many contact binaries there could be so many contact binaries in the Helios. So I was wondering, what do you think about it?
I would love to do that. But I sort of feel like the cold classicals is a big enough problem for one person to tackle. And so, hey, why don't you go work on Helios? Use the same techniques. It would be great. We just have, that's the cool part where we're at now, because thanks to Gaia. You've got these questions. We don't have to wish we could learn it. You just have to be interested enough to do the work to actually make it happen.
Anyone questo?